Alright, so this is the beam spot size measurement, part of the experiment. Get a chair. So we've got our laser through the Faraday isolator. So again, this is a practical device. Maybe I haven't mentioned it. This is a practical device to stop light going back into the laser head and destabilizing the laser. You want the laser mode to be ejecting the same Gaussian mode, right? You don't want the frequency of the Gaussian mode to be changing. There's a cavity inside there, right, that makes resonant a certain Gaussian mode of a certain order. But if you have this light coming back into the cavity, then you can get some interference effects inside, and for that reason we have this component to stop light from hitting some face here and then actually going back in, and you can also get interference, between here. So the next component, we've got a polarizer, and that's just so we can filter out some of the power before the light gets to the photodetector here, because this photodetector has a maximum intensity that it can, or maximum output current from whatever intensity you put on it, and which corresponds to a voltage of about 11 volts. So you can't, once it saturates, you can't measure any difference in voltage. So we've got it taken out some of the power here so that we can resolve the intensity changing as we gradually block the beam, okay? So you should have read the manual and have an idea of what I'm talking about, but essentially we're going to measure the beam at this point, because this is what's going to block our beam. So all we do, we get some screws, and we fix this to the table. This is a translation stage, and down here on this side, oops, try not to do that, although it does happen quite often, unfortunately. So we fix the translation stage to the table. I like to get both screws in, because if you fix one all the way, then you may not be able to fix the other one all the way. You need to give it some wiggle room. Alright, so here we've got a translation, the micrometer, which will give us a very precise measurement of how much we've translated this beam block. So the idea is, because the beam is a Gaussian profile, we know that as we block part of it, we know how the recorded transmission should respond, right? We know what the distribution of a Gaussian is. It's strongest in the middle, and it tapers off as you move away from the beam center in a Gaussian fashion, described by a Gaussian function. So as we then sweep across this Gaussian function and just block it, we know what we should expect to record. Okay, so that's what all the theory in the optical cavity lab manual is saying. So I just get to the point where I'm close, when I can see this start to block the beam. I'm not there yet. Almost there. Alright, there we go, so now I've got it. So look, the shape of this thing is not important. You may have thought the beam's got to go through here. It's got nothing to do with that. We just need a knife edge, so I could even tilt this and refix it. I'll have more range now. Now I can go all the way back. Now this is my knife edge. So now I know I'm just before it's going to start clipping, so I want to record my voltage here, and then I can look at this and say, alright, I'm going to move it 0.5 millimeter, or 1/4 millimeter, or whatever you decide to do. I mean, the beam is only going to be a few, like 1 millimeter or so big at this point, so you'd probably be wiser to take smaller deviations. This micrometer can measure hundredths of a millimeter. Okay, so it's very precise. So we'd have resolution taking 17 or so, 20 measurements over one beam. We record all those intensity values for each position from some arbitrary reference point. So I'm going to start. Where am I going to start on this one? So the beam box around there. So I'm going to start back here. So I'm on or it might be better to do, instead of sweeping across it, I'll fully block it and then go back. So I'm probably going to do it that way. So I'm starting on 5, 6, 7, 8, 9 millimeters and 5 1/100ths of a millimeter. So 9.05 mil. Bam. Now I'm on 45, so I'm 9.45 mil. I can take another reading on my oscilloscope. .9, 10.2. You get the idea. So we're measuring very small increments of millimeters. I'll just show you what I'm looking at on the oscilloscope. Now I've got to turn off the lights. To unblock. So as I unblock the beam, so let me adjust the range. Hopefully you can see that. So I'm looking at the blue channel 1 I can just turn off. And my voltage is 1 volt divs. And we can see we've got a constant intensity on the photodetector roughly. So that's what I expect to see. And now as I gradually unblock the beam, that intensity is increasing. Quite quickly really, because the beam's so small. So here I would measure the height. I can put a measurement on my oscilloscope. I'll measure the max voltage. I don't really want to trigger. Alright, so I'm at 3.84 volts now. Just adjust this the offset. Then I can move my thing a little bit. 4.16, take a measurement, take the voltage reading and also take the position reading, move it a little bit more, take the voltage, take the position, move it a little bit more, take the voltage, take the position, a bit more, until it stops moving, okay? So that's what your data is going to be composed of. And I'm going to do that at 6 different, or maybe, yeah, around 6 different positions with the knife edge. So I'm moving the knife edge. The position of the photodetector doesn't matter. I just need to be able to pick up the light, make sure I don't lose any of the light. So that's one position. So I'll mark that here, you know, here, that's my position. I'll do another one here, here, here. Once I get to here, I obviously have to move the photodetector, here, and then I measured the beam spot size by fitting the data I've taken at each position. Okay, so that's how it works. That's the idea. Yeah, so that's the first part, and then I'm measuring this distance, you know, like where this position is from some arbitrary reference again. So maybe here, I can measure from here, and then I'm going to calculate where the beam waste from this laser is relative to this reference distance, okay? Because we need to talk in terms of some distance from something. It could be anything. I could say from here, that's my reference, and say, you know, this is 15 millimeters from there, 15 centimeters from there, something like that. Oops, knocking everything. Setting a very bad example. You need to be more careful than I am in these labs. It's because I'm filming at the same time. Yeah, so that's pretty much everything. So measuring the distance from an arbitrary reference. This also has an arbitrary reference where we start sweeping from. So in all your fits, you're going to have to take into account some arbitrary reference, like you're not sweeping from the middle of the beam, you're sweeping from one side to the other somewhere. So you just put in a variable to account for that, a parameter to account for that. Okay, that's it.